So I was doing some more reading about what the solution we came up with, and I actually realized I was wrong at the end of the last video. So I wanted to come back online real quick to make a correction. So for those who are watching the video on demand later and go, WTF, it's not cyclic replacement, I wanted this here so that y'all could see that, yes, indeed, I figured out it wasn't cyclic replacement. So cyclic replacement is a completely different algorithm where it's a little bit more complicated and the proof is a little bit more complex, but the idea is more or less you're putting the values into their final place by counting, around the list until you get it to the right spot. It's a little complicated, and I'm not going to really go over the solution today, but I just kind of wanted to more espouse that our solution is just truly doing reverses, and it's actually, I think, proof-wise, it's a little simpler to explain than even cyclic replacement was. So I'm going to try to see if I can grok out together real quick what the solution should have been. So let's take a quick look. So suppose we have a list of 1, 2, 3, 4, 5, and the number of rotations in this case is equal to 2, which would be k from the problem's perspective. But that's totally fine, right? So the answer to this problem should be, so let's just do the rotations real quick because it's late and I want to make sure I don't make a mistake. It'll be 5, 2, 1, 3, 4, and then it's going to become 4, 5, 1, 2, 1, 2, 3, right? So this is the solution. So what do we note that is unique about this? What is uniquely happening here versus here? So to kind of help out, I'm going to kind of bracket the parts of the array that stay together, and I'm going to use basically different things to kind of notate different stuff. So what we see has happened is something like this. Okay, cool. So if you look at it, what's interesting about what's happened here, if we look at just philosophically, well, not even philosophically, it's probably the wrong word to say, but like practically when we look here, what's happened? Well, when we go from the start and then to the final, after the final rotation to the final state of nums, what we've noticed is actually all that's happened is that the back half of the list, which is length 2, which is equal to a rotation factor, has moved to the front of the list, and then essentially the front of the list, which is going to be the length minus r, so 5 minus 2, which is 3, then moves to the back half of the list. So this kind of goes to here, and this kind of goes to here. So I believe the way this was derived, so I think the way this solution was derived is probably someone did cyclic replacement, they did a brute force, they looked at the solutions and went, wait a minute, if I look at this intuitively, all I have to do to get this is somehow get the length of the array minus k, obviously subdivided down with our hack we previously talked about in the video, off to the right side of the list. And then to the left side of the list, we basically need to take the length minus 1 minus k, those two indexes, and push them to the front of the list. So they asked themselves, well, how could we do that? All right, so if we just simply try to take 1, 2, 3, 4, 5, and we try to do some sort of movement, well, it would be kind of hard, right? Because we can't just reverse the front half, right? So just reversing 3, 2, 1 and then doing 5, 4 gets us nothing, right? Because we did not get to 5. We didn't get to 4, 5, 1, 2, 3, which is the result we want. In fact, I just actually did the algorithm that we did before, right? I kind of just did it in one step, which is, I think that might be a coincidence, y'all, which is why we actually got it right in the last problem, but that was a pure coincidence that we got it right. So just ignore the fact that this worked. That was a pure coincidence. But we wouldn't necessarily get the right answer at this point. So I think what they realized was that we know we need to get the back of the list to the front, and conversely the front to the back. So that's why that first step is critical in taking 1, 2, 3, 4, 5 into 5, 4, 3, 3, 2, 1. So at this point, they're not in the right order, but if you look, this set contains 4 and 5, which is what we're wanting, and then the back half contains all the numbers in this section, 1, 2, 3. So at this point, it's like, well, they're almost there. So all we have to do is reverse both subsets, and we get 4, 5, 1, 2, 3, which is the answer, which is very intuitive, right? So essentially, we know just by inspection from the start and the end that we need to pull this portion to the front and this portion to the back. Well, using simple array methods, in this case two-pointer approach, we can start by getting them roughly in the right place by simply just reversing the entire list. Then after that point, it's just a simple matter of rotating each of these subgroupings then to match this. And I think that's how the reverse approach might have been intuited. Now, I don't know, of course, without asking the original finder of this or looking at his mathematical proof with probably all sorts of good asymptotic analysis. But I think intuitively now I kind of understand where this could have been derived. And I hope that helps. I'm so sorry for mentioning cyclic replacement. I was wrong. I apologize. But I hope this at least better explains kind of what we ended up doing, which is actually kind of a cool method that honestly I don't think you would think of necessarily approaching this problem. I'm guessing it's more likely you would brute force or maybe even approach cyclic because, yeah, this is just inspecting the problem and then finding the algorithm, which is a valid way to find algorithm. It's just not one you would necessarily think, unless you've probably been working on this a while. Anyways, thanks so much again, and have a good night or day once again. Bye-bye.